Welcome to the Todd and Noah show, taking the mystery out of electric motors.
Sounds very scary.
Sounds scary. Once again, we have Noah Bethel from
Sunny Tampa, Florida.
VP of Product Development, broadcasting in
Sunny Fort Myers.
kind of sunny.
Yeah,
it's rainy season down here. You never know what you're going to get.
Drove in and out a little bit.
Yeah, we were in and out of thunderstorms as we trekked our way down here.
Fort Myers has a history of strong winds, and
hurricanes hitting it as well.
We bring only sunshine.
We try to bring positive energy and vibes. Well, Noah, this podcast is going to focus on case studies from the field, a forensic review focusing on power circuits.
Power circuits is a big deal. You know, the studies we've read indicate that as much as 10% of problems can come from the power circuit. And that's
the power circuit also reduces efficiency, right?
It absolutely does. It's a big part.
And when you're talking about higher utility costs, higher utility bills, you want to be as efficient as possible.
Absolutely.
So if you have a high resistance connection, or if you have a current imbalance or voltage, that's just unnecessary heat inside that power circuit, which then detracts from the power.
Waste.
It's wasted. Mm-hmm. Exactly. So we've got some great case studies from the field that we're going to dive into, do a forensic analysis of. And some of them are really nice because by actually understanding the data, it may not point. A lot of times power circuit doesn't mean it's a motor issue.
Absolutely. Yeah, and unfortunately, we hear this over and over again that replacing or repairing the power circuit is one of the more expensive, time-consuming parts of it. So, unfortunately, if you're Easter egging, as we've all had to do in certain situations where you don't have enough test data to make the right conclusion, the easy thing is replace the power system. So you replace the starter or the drive, and when that don't work, then you replace the motor, and then pull the cables and redo the cable run. And that's a big deal. We understand
it's a huge deal.
It's a lot of time. It's a lot of resource. But if you don't have time to do that, you certainly don't have time to replace the drive and the motor when that's not the problem. So you want to make sure you're doing root cause. If it is the power circuit, that's what you want to prove that it is.
I think Easter egging is a term most people may not know, but in the military, Navy especially, they didn't like you to do Easter egging when you were troubleshooting. That's just, you have no real set agenda of where you're going. You just say, I'm going to look over here.
Yeah.
I'm going to go look over here.
It's guesswork.
Mm-hmm. Essentially, you're just guesstimating where it might be. So this company or this technician sent us and saw some online high current and voltage imbalance. Well, that alone tells us something there, right? When you get a current and a voltage imbalance and you're in the MCC, that starts to fine-tune our thought process,
right?
Correct?
You've heard us talk, if you've been listening to our podcast or our tips, you know that voltage is very specific. It's location specific, right? So where you hook up the voltage leads and run the test, it only looks upstream.
Yes.
Right? It does not look downstream. All right. So you know that if you're measuring something and you have a relatable, voltage and current imbalance, it's throwing a flag up, you're probably looking upstream from where you're connected. Again, current looks downstream and upstream, right? So it's kind of a universal indicator. So absolutely, this is telling us something.
Right. And so good troubleshooting practices would tell us, okay, if we're downstream of the contactors, we're on the load side. Mm-hmm. So we're going to test it and we see a voltage and current. What should we do next? Should we go upstream on the line side? Can you get up to test voltage and current? Is that possible?
You can.
Or is it difficult?
So it can be. You got to be careful that you're not, bypassing certain safety things, right? So generally there's some place above the contactor you can gain access to, hook up to, with the voltage up there. You don't need to move the current, right? Current's universal. But
right. But so that current imbalance would exist regardless of where you're at on that circuit. It's
whether
always
you're downstream the contactor, upstream the contactor. And so not a problem. But voltage, if you go upstream of the contactor and the problem goes away, Well, now you've just identified the root cause, which is the contactor itself. When I say be cautious, you don't want to go above the fuses without some precautionary issues. Now, like our technology is built in with, quick blow fuses and protection and stuff like that. So if something did go wrong, it should take us out of the circuit before anything else happens. But just messing around upstream of fuses and stuff like that from the line side of the whole switchgear, it's not recommended.
Okay. So they did line side Emax testing and the voltage imbalance went away.
Interesting. Just like we just mentioned.
Just like we just said.
So we went from below the problem to above the problem.
Yeah.
And now we're really zeroing in on what's going on.
So load side, it showed voltage and current imbalance. Now offline testing showed resistive imbalance, but it depends on where you're testing offline, correct?
Right. Resistance is much like voltage. It's specific as to the connection. So because MC is an active test, we're not just passively acquiring voltage and current. When you connect it and you turn it on for a test, it sends signals out of the leads and it goes to the connected source or to the connected supply, which is the motor. Whether it's wire delta connected, it runs through the conductors and the windings and comes back. Right. So absolutely, if you were downstream of the problem and you ran an offline test, you would not see it
at
all.
Not at all. And in this case here, I think if you're at the T leads,
0.1%,
you wouldn't see it.
No, they didn't. 0.1% resistive imbalance. That's very good.
Didn't see it at all.
Yeah.
So what they then determined is it's not a motor issue, which is in itself very important to not pull a motor.
Yeah. Fault zone number 7, it's not the motor.
It's not the motor.
That's right.
Right. Yeah, you're really pushing for that 7
I know,
fault zone, aren't you? But what they found was if you would have had to pull the motor, cost savings, it would have costed about $175,000 in production loss.
Wow.
So by saying, no, it's in the contactor circuit, which is a relatively quick fix.
Compared to a motor replacement or a cable run? Absolutely.
Relatively quick fix. Replace the contactor, and then it's good to go. We also had, I'll take you to another case study that we may not talk about in here today, but we had almost the same issue where somebody, they shut the starter, right? And the current was fluctuating.
I think I know what you're talking about.
Up and down, up and down, up and down, up and down. They thought it could be a rotor problem, but we always talk about, they say, let's send it to technical support at PDMA Corporation. Let's have them look at it. And the tech support team did an excellent job and said, listen, we don't think it's rotor related that's causing the cycling.
Right. Yeah. Freaks you, it makes sense.
The thing of it is, where are most motors? They're not in the quietest of places. A lot of times you go into a plant, you have to have ear protection. So not only is it loud, but you also have ear protection in. So you had to essentially get really close to that starter to hear what was happening, and it was the contact chatter.
I remember that. Yeah, we dealt with this occasionally on in the Navy, where you'd have 3-phase contactors and you'd have shading coils. The idea is to prevent the voltage from going through zero, and as a result of that, you have a sudden drop out of the contactor and it's chattering. That's exactly what you were describing, right? So by adjusting or replacing a closing contactor or a closing supply or something, they were able and to fix that without replacing a motor. I mean, my gosh, the savings of $175,000. Someone deserves a bonus.
Yes, they do. You're absolutely correct. Somebody deserves a bonus.
I think so.
You bring up an excellent point, and we say this all the time, is if you're in the reliability industry or the field, or you're out in the field doing testing, and you find something, right? Because that's what your job is, kind of to find problems before they become catastrophic so you can fix them so that they save you money. We have to, it's almost when we have people come to our training class, we have to remind them how important it is to recognize your saves.
Mm-hmm. I think we had a tip series called Justification.
Yeah, justification. Justify what you do out there.
And you know who has to justify the most? The guys who have their plant running at the premium condition.
Optimum.
Yeah.
Because it's rare that they find anything.
That's right. They find it early enough, it doesn't affect production, and then you get new management that pops in and occasionally like, well, what have you done for me lately? Everything.
Yeah, everything.
We've got you making money like this. So you're right. Justification is critical. When you find something, you save $175,000, it's something to put on paper.
It's hard
and
to
share
toot
it.
your own horn, but it's a necessity in order to bring a light to the department that, hey, we are valuable to your facility.
And remember history, right? Go back and look at the annual maintenance cost associated with running an unreliable plant. And, because if you have cut the maintenance cost down by 40% and you've been running at that lower for 10 years and you've never known, new management doesn't know that there used to be 40% more expensive. Well, it's hard to say, well, that's what we're keeping from, right? We don't want to go back there. And so if you want to continue it, it's a cycle.
Yeah. So this next case study really just highlights, you do a standard test and the importance of that standard test. And we used to go out and say, is 3 minutes too much to ask to find out the health of your motor? And in this case here, is 3 minutes too much to ask to find out that you have a very high resistive imbalance in the circuit? Now, this was taken at the MCC, and they found a high resistance connection. So what they did is what we always tell them to do, isolate the power circuit from the motor. And when they went to go down and do that, open up the box. What do you see usually? Sometimes you see water.
Occasionally, a rust line, a couple inches up that didn't come from the manufacturer.
Or you could see a bunch of tape.
Ideally,
and then disintegrated.
Tape. Oh man, these pictures for those of you who are driving and listening. These pictures are amazing. It's almost like someone grabbed the tape lug and pulled, and it just crumbled.
Yeah, it's kind of like on the Mummy.
It
when
does
you touch
look like
the
a
mummy.
That's exactly
right
what it
at the
looks
end, and he just disintegrated into.
That is exactly what
paper.
It looks like. It's. I'm surprised it hadn't failed much earlier. So this is a severe.
It was being held together. Listen, electrical tape is strong.
It is good stuff.
Okay,
right? Especially EB red. That stuff is amazing.
That's amazing. It can keep you. Listen, if you're in the field and you break your leg and you got some of that with you, that might be able to splint you back together.
On a submarine, we used to call it.
You
ready for this? We call it super glue on paper. I mean, it was that good.
Super glue on paper.
It was. Not
only
you
guys had so many issues on a carrier. We had nothing really happened that way. Our job was to just
something
launch
about underwater and
I guess
saltwater and electrical. I don't know.
It just doesn't
my
go
boat was
together.
commissioned in 1962.
So mine was in 1992. So
maybe we had
30-year difference.
A little bit of an older plant. But if we didn't use the tape to fix and repair motors, you could also tape somebody up on the wall with it. That's how good it was. It was that good of tape.
Not that you ever did that.
Not that we would ever do that. No.
That you would ever do that. So this next case study comes to us from overseas, actually.
Oh wow! I see the Philippines.
Yeah, it's overseas, and it's about really this power. So you have induction motors, you have wound rotor motors. Wound rotor motors are interesting in that they have a little bit extra. They have a resistance bank.
Yes.
For startup.
Yes, I mean, we enjoy testing them mainly because, usually on an AC induction motor, it's a squirrel cage. You can't actually send anything onto the rotor, right? It's totally induced and you got bars and that's it. In a wound rotor motor, it's the same induction principle, but instead of inducing into a cage of bars on a rotor, it induces it into windings on the rotor, which are connected to resistor banks, and then they're variable, right? So a lot of times
because they're there on startup to minimize current, and then as that rotor is rotating up to speed, they cut those.
Exactly. They're all shorted out of the system by the time it's up and running. Now, keep in mind at the end of the startup, sometimes there will be a variable resistor for speed control of like a crane. Crane's a popular use for wound rotor motors.
And does it also have brushes and slip rings?
So yes, one of the big magic troubleshooting spots of the wound rotor motor is the brush connection between the rotating, rotor windings through a 3-phase slip ring out to the resistor banks.
And that's how
we would access it, yeah. So if it's offline, you're going to go in. You're going to isolate the resistor bank connection. So you'll pull the brushes. You'll send signals into the rotor and get all the testing on the 3-phase rotor windings. Then you'll send the same signals, from the MCE into the resistor bank and test them as well. Now, certain things you don't care about. You don't care about the inductance of resistor banks, and so that kind of is something you can overlook. But yeah, the nice thing is the fact that you can separate into 3 separate components. Root cause failure analysis is usually pretty good. Yeah. Now, let's talk about while the motor's running, right? While the motor's running, Well, now we're wanting to do inrush startup on the stator windings. Occasionally, we'd like to get an inrush startup of the rotor windings, right? With the new PDMAI system, that's something you can do. And that's very powerful because of the amount of current that's flowing through and just watching those resistor banks cut out at the right time. Right.
Yeah.
So when that's all automatic. So when the contactor closes to cut out one set of resistors and then it moves from one to the other, that has an immediate effect on the current. And you can see that. You can see it good from the stator. You can see it great from the rotor.
Yeah.
Which is fantastic.
So let's say that this asset has a pole pass sideband. Can you trust that pole pass sideband in a wound rotor motor because there's no rotor bars?
And the answer is yes. Now, because it's not your classic squirrel cage rotor, we want you to be a little bit flexible on the warning settings, right?
Okay.
So, right, we have a classic sort of like a 45, 36 caution and alarm. We much prefer you establish that after the baseline. So get a capture, verify the speed, and then establish the height amplitude warning settings on the pole pass frequency, which is, going to be to the right or left of line frequency. After you've established normal healthiness, establish a normal run, then establish the warning settings.
Okay, so they came in and they did a current signature analysis and they see an elevated pole pass, and they also see that they looked at speed in October, and then come January, speed dropped dramatically.
Right. For our quantitative listeners, we have a nameplate speed of 880 RPM.
Yeah, so that's full load amps.
Full load.
880 RPM.
And at a low load, 60%, we're seeing an 892. Now that makes sense. If full load's 880, synchronous is 900. When you have an unloaded motor unloaded to around 60%, you'd expect something higher than 880. And we're seeing 892, but we do have a pretty elevated pole pass sidebands here.
Right, and so the next test we're almost at 60% full load amps.
Which is exactly the same as the previous test.
And we're below full load amps.
This is not good. This is not a good combination. So same exact load.
Yeah.
Lower speed by what was the actual?
892 to 878.
That's a significant drop.
That's a significant drop for the same loading.
Absolutely.
With a high elevated pole pass sideband.
Even higher. I mean,
it's almost equivalent to the 60 hertz or 50 hertz.
Right. So the normal history of this would be you would think, okay, we got elevated pole pass frequency, we got bad rotor bars, but we don't have rotor bars in a wound rotor motor. We have windings. So now we start to worry about the three-phase winding.
The circuit.
Yeah, because the rotor's wound three-phase. Right. Mm-hmm. So we would be concerned about the circuit. Like, is there something's wrong with the winding? Something's wrong with the brush communication? Something's going on with that rotor circuit for sure.
So we're going to look at brushes. We're going to look at brushes. We're going to look at the actual windings in the rotor itself. Correct.
Resistor bank cables out to the resistor banks. Absolutely.
Yeah. So now we also just did inrush current, and we saw a huge imbalance in our current. Right.
From the stator.
Yes.
Yes.
So that was through the stator.
Yeah.
And that's a massive, why would that change in the stator like that? Is the rotors rotating and that's what's causing that?
Right. So imagine just like if you had broken bars, if you have a defective rotor circuit, right, whether one of the three phases has become defective, it's going to be a rotating variable magnetic field, right? So rather than nice, even balanced influence, you're going to get this this heavy reflected impedance back on the stator windings, just like a broken bar.
Yeah.
And it's going to modulate the stator current.
So they saw all of this and they're like, well, let's also bring in thermography. So they went to the brush rigging itself and they saw a massive change in temperature on one of those brushes, one of the phases, which would cause that massive swing in current.
Right. For those driving, we're looking at, melting, screw heads that are effectively holding the brush holders down. They're starting to melt.
So what they came of in a significant heating, what they found was it was just a bad brush, improperly seated.
Right. So effectively, if you think about a three-phase, let's say a dual delta wound rotor on a wound rotor motor.
So if it was, let's say it was 60 bars.
Yeah, effectively you're taking out 20. And maybe not taken out completely, but affecting them in a way that it's massively affecting. I think the pole pass that we were seeing earlier, it's almost as high as line frequency. We're talking about the sideband frequency, which is normally, we consider it bad when it's 40 decibels away, from line frequency. This is almost as high as line frequency. It's really bad. And what a great catch.
Yeah, and so once you find the catch, they went back and did all the post-repair data. Everything changed back to normal. All of the pull-pass sideband, all of the typical
no modulation on the
stator current.
It's huge.
No thermography. Basically high temperatures on one of those phases. So I guess wound rotor motors can act much like a power circuit in a way, because that's what you're dealing with. And they're used in cranes, they're used in elevators where there's heavy torque requirements.
Yeah.
And you'll find them just about most cement industry we come
Cement
across.
always has them, linked to certain pumps and compressors and things. I get a $700,000 savings here.
Now that's in a foreign currency.
Yeah, well,
which is 55
you guys do
to
the homework.
1.
No, you guys do the homework at home.
700,000.
That's all I want to do.
Is there a USD there? No,
there's
not a USD there. So it's in a foreign currency. So
a great savings.
It's a great case study on a wound rotor motor. We don't get a lot of those, but it's always excellent to see how our technology can assist with something that can be prevalent out there, the wound rotor motors.
Yeah. Well, and it's interesting because that was just the repair costs that they avoided. The loss of production is the big killer.
Yeah, isn't that sometimes that's where the main cost is at? It can be the smallest of motors, but if it puts production down for a couple of hours, half a shift.
Oh yeah.
Or the night shift or a full shift, you're talking now, it could potentially be millions of dollars.
What was the word you said? Justification?
Yes.
Write it down.
Right. Justify. Now, this last one here that we're going to walk through today, I think it's a multiple of different types of things that were found. This is a 460-volt motor. They're just as important to us as 4,000 volts.
Many times the workhorse of the industry.
Yeah. High resistance connection. And it's hard to see because we're talking about numbers 0.01126, 0.01199, 0.00994. We're talking minor differences. But when you do the imbalance, it's pretty significant.
It's 0.002 of an ohm, and it makes a big imbalance.
Yeah.
Yeah.
It makes a big difference, and that difference is it creates excess heat, and that excess heat over time degrades. And in this case here, the picture that you're looking at, which is the end result of that resistive imbalance, is substantial.
This looks like lightning struck the insulator.
Yeah, it really does. It looks like somebody put a laser.
And the laser's a good example, yes. It's explosive.
Lasered around that.
The interesting thing is, that can occur. And if there's not a ground connection somewhere near that, ground won't necessarily show that.
Yes, right. That's the biggest thing is you do a resistance to ground.
We joke that, we used to be asked to save the world with a
fluke and a megometer.
Not a
multimeter and a megometer,
right? And it's good, but it's not everything. In this situation, resistance to ground testing would not have seen this. But in a resistive imbalance situation where the heating was internal and only started to arc through the X side of it was just an incredible picture.
Yeah, and so after you repair it now, they're down to 0.00989, 00987, 00984. Very low.
They dropped 2,000s.
Yeah. And so now you set that as your new baseline, and you go on your merry way. $30,000 to replace that motor. And it was just a power circuit.
Yeah.
It's not a small bill.
It's not a small bill. And, it's probably...
If you don't have to pay for it.
Right. And depending on productivity, it might be small compared to the loss of production, for sure.
So this next one was the nameplate is 4160. And this could happen because this was a used motor. It was a booster pump on a pipeline found during routine vibration checks and audible noises. It was purchased as a used motor classified as electrically okay. Mm-hmm. I'm not sure what that means, if there's a terminology that if it's electrically okay, it's certified to this
standard
level.
that is labeled electrically okay. My guess is that was just the local accepted thumbs up.
Yeah. So they did what's called a rotor influence check. And if, for those of you who don't know what a rotor influence check is, I think we've explained it in our rotor tips, our rotor case studies. We've talked about a rotor influence check. So if you want to, you can listen to those podcasts. But in this case here, we did a rotor influence check, and it shows clear signs of a air gap or eccentricity with this asset.
Right. Now, we always recommend be careful depending on the type of bearing you're dealing with. If you're dealing with an oil bath bearing, journal type stuff, de-energized, sometimes it can settle. Right. And if that's the case, some
the oil, if it's
absolutely
just kind of sinks down and then
it'll settle.
Which means the stator is a little bit closer to the
rotor will settle one
stator.
way or the other. Vertical motors are notorious for this, and so just be aware of that. And so a lot of times, if we've had some people on the larger horizontally mounted journal bearings, they'll actually temporarily turn on the oil pump, which lifts it up, and then they'll do a Rick test like that, to make make sure they're not
just
getting
to
that.
Float it.
But this was a classic example, and if you think about it, the rotor should be centrally located, center line with the stator center line, and if they're not, then you're going to have the rotor a little closer to the stator windings, and as a result, you're going to significantly modify the inductance value. Rotors closer to the stator normally elevate the inductance value. In this situation, as they turned the motor, the overall value of inductance rose, and that's kind of a big deal.
Yeah. So they took it to the shop, and they found that this rotor was out by 30 hundredths of an inch.
300ths, yeah.
300ths of an inch. That's significant.
It can be a big deal. Absolutely.
It really, really can. And so they had to fix
10
that.
thousandths is a number that
Such
is
small tolerances
is,
now with these higher efficiency assets. You have a very limited amount of room to make a mistake in. And this was pretty substantial for this asset. Now it's 480 volt. It may not be a high efficiency motor, so it may have been okay. They did the Rick on it, and everything came back to normal.
much better looking, yeah. Very balanced, peak to peak. So as they turned the
balanced.
rotor and measured stator inductance values, that it's like a perfect sine wave.
Yeah, so once again, just kind of highlighting how really simple things, if left unchecked, can become expensive things. And in this case here, you see it early, that eccentricity, you fix it, you put it back together, you fit it correctly, and now it's probably, not only is it electrically okay, but it is okay to put it into service. And the other one, it was just a resistive imbalance, $30,000 motor if you needed to replace it.
It's time for a C story. So we're doing. This is a real sea story. When I say real, meaning we were at sea, not on a submarine, but on an oil platform.
Oh, okay.
Yeah. So, and let me say this is a partial sea story because we were only partially at sea. Okay, so we were called out.
Did you take a dinghy to get there? How did you get there?
There was a big
helicopter,
long, like a big long, strung together.
Pontoons?
Well, like some kind of floating vessels.
Yeah.
Effectively that we walked across. And then
to a platform.
There's an oil platform that was being put together and commissioned off the coast of Texas.
Okay, so it wasn't out in the ocean, was it?
It was in the ocean, just at the near land.
Near land? What does that mean?
Well, it means we were walking out to it. So we walked out and caught these elevators to go up to the platform, and we were doing a baseline run for the company, so that they had all the smart, right? Do all the baselines on, again, a lot of times, the people who own the platform aren't necessarily owning it initially.
Yeah.
So whoever's manufacturing it, like a large manufacturing company will make it and then turn it over to the owner, right? Same with the plants. So we're doing all the baselining, and we're finding high resistive imbalances and hot spots with thermal cameras over and over again, right? And we finally figured out that as we looked into it, because initially we were just doing MCE resistance measurements, high resistance connection, high resistance connection, high resistance connection. We finally opened up the cabinet. Well, the fuses that they were using for the switchgear were bought in the States, but the switchgear was built in Italy, right? They didn't fit. They weren't the right size. So instead of getting fuses the right size, they actually put like little extender jackets on the outside of the fuse. Well, 50% of those were not connected enough to not create a high resistance connection. So note to self, if the fuse don't fit, get a new fuse. You thought it was going to rhyme, didn't you?
I thought you were going to go down the O.J. Simpson.
Yeah, no. No acquitting. There's no acquitting. If the fuse don't fit, you need to get a new fuse.
All right.
Don't
That's
extend the fuse.
That is good information.
I thought it was very applicable.
Well, that brings us to the end of this case studies from the field, a forensic review of the really power circuit anomalies and how those small things can potentially become large things if you don't fix them early and you don't get them early. As always, we appreciate you guys listening to us, and if you have any case studies you'd like to share with us, we'd be more than happy to entertain them and see if we can use them. We always like to educate our customers or educate the people who follow us on our YouTube channel or our website or whatever vehicle streaming that you listen to us on. So that'll be the end of this one, and we hope you guys have a great day, and we'll talk to you real soon.